Describing sound. Now that we know how sounds are generated and how we hear sounds, we need to be able to describe the sound in a logical way. There are two fundamental characteristics of sound. There's the sound frequency, which corresponds to the subjective pitch of the sound. So that means low rumble sounds compared to high-pitched squealing sounds. On the other hand, we also have to describe the amplitude of the sound, which corresponds to the subjective loudness. So basically something that is quiet versus something that is loud. So let's look at frequency. Frequency is basically the pressure variations per second of a sound and is measured in the unit of hertz. It is related to the wavelength of sound by the equation on the right-hand side there in terms of the speed of sound. The speed of sound is 344 meters per second and it is constant. There are slight variations around the world on 344 meters per second, and it is best to check in your part of the world what the actual speed of sound is. So the relationship between frequency and wavelength is speed of sound is equal to the frequency multiplied by the wavelength of the sound. So if you want to calculate the wavelength of a certain frequency of sound, the wavelength equals the speed of sound divided by the frequency of the sound. Our range of hearing is from 20 Hz all the way up to 20,000 Hz or 20 kilohertz. The common range of expressing sounds for engineering calculations is 20 Hz to 10 kilohertz or 10,000 Hz. So the corresponding wavelength of sound for a 20 Hz frequency is 17 meters. For a 63 Hz sound, the wavelength is 5.4 meters. For 500 Hz, the wavelength is 68 centimeters, all the way up to 10 kilohertz where the wavelength is 34 millimeters. So as you can see, as the frequency gets higher, the wavelength gets smaller. So very high frequency sounds have very small wavelengths. So let me play you some different frequencies of sounds. First of all, I'll play you a 63 Hz tone or single frequency, which has a wavelength of 5.4 meters. Next, I will play you a tone at 1000 Hz, which has a wavelength of 34 centimeters. And lastly, I'll play you a tone at 10,000 Hz. Now, depending on your headphone quality or your playback system, you may not hear a sound at 10,000 Hz. So see if you can listen to this one. Let's consider the different wavelengths of sound at the different frequencies. Let's look at 63 Hz or 5.4 meter wavelength. If we were to try and absorb that frequency of sound, so to try and reduce that sound level within a room, we would need a material in the same order of magnitude of thickness in order to absorb that sound frequency effectively. So think about a 5.4 meter wavelength. You would need a piece of material, absorptive material such as polyester, in the order of meters to absorb that sound effectively, which is very difficult to do. On the other hand, if we look at 1,000 hertz, which has a wavelength of 34 centimeters, we need a much thinner piece of material to absorb that sound effectively. So consider that when you are trying to design a room to absorb low frequency sound, how difficult it would be because of the size of the wavelengths involved. And this is a very common problem in acoustic engineering. We have just listened to single frequencies or single tones of sound. That's what you see on the top of this slide, where we have a pure tone. It's a single wavelength of sound. In a sound level versus frequency plot, it would stand out as one single frequency. If you consider a musical tone, which could be the pluck of a string of a guitar or playing a note on a piano, a musical tone is made up of that fundamental frequency of sound or that tone of sound, but it has higher harmonics included in the fundamental, which are a multiple of that fundamental frequency. So a musical tone is made up of the fundamental frequency and higher harmonics, which are higher frequencies or multiples of that fundamental frequency. Common sounds, which include music, speech, traffic noise, aircraft noise, these include many frequencies of sound of different magnitudes or of different loudness levels. As you can see on the right-hand side there, the sound level versus frequency plot would show many frequencies of sound with different sound levels at each of those frequencies. This is called broadband sound or broadband noise. Because common sounds are made up of many frequencies, we need a way of summarizing the sounds that we hear into different frequency bands. Like I said before, the range of hearing of a typical human is 20 hertz to 20,000 hertz. So that's nearly 20,000 discrete frequencies that we can hear. So that's a very large range of sound frequencies that we have to describe. The way we describe sound and the way we summarize it is to break it down into bands, octave bands or third octave bands. And as you might expect, octave bands breaks up the typical range of hearing or the typical range we use for engineering into 8 bands with center frequencies. So the octave band center frequencies that are known internationally start at 63 hertz, go to 125 hertz, then 250 hertz, 500 hertz, 1 kilohertz, 2 kilohertz, 4 kilohertz, and 8 kilohertz. So the center frequency basically summarizes all the frequencies that fall below and above that center frequency. To get higher resolution, we often use third octave bands. Basically, what we are doing is splitting each octave band into 3 third octave bands. So for instance, the 63 hertz octave band would be made up of the 50 hertz third octave, the 63 hertz third octave, and the 80 hertz third octave. So these are convenient ways of summarizing all the frequencies that we hear into different bands according to the resolution that we need for our calculations or for describing the sound. Let's switch from frequency to sound pressure level. And how do we describe the sound pressure levels that we hear? Like frequencies, we have a very wide range of sound levels that we can hear, or sound pressures that we perceive at our ears. And this can range from 0.00002 pascals or 20 micropascals all the way up to 100 pascals, which is a huge range. This linear scale is unwieldy, so we need to find a more convenient unit of measure for sound pressure level than pressure itself, or pascals. Because our ears respond logarithmically to sound, which means basically we hear different sounds at different sensitivities. When you heard those tones earlier, your ears were probably more sensitive to those higher frequency sounds like the 500 hertz or the 1000 hertz tone than they were to the 63 hertz tone. So this basically means our ears respond logarithmically to sound. We can therefore derive a unit called the decibel, which is a logarithmic ratio of pressure squared to a reference pressure squared. And that reference pressure is basically the lowest pressure that we can hear. Therefore, the decibel can be derived, or the sound pressure level, as 10 log the pressure squared of what we hear divided by a reference pressure squared, or the minimum pressure that we can actually hear. And in this case, it is 20 micropascals. So now that we have the decibel as our unit of measure of sound pressure level, here are the typical sound pressure levels that we hear in life. In a bedroom of a country home, the typical sound pressure level might be 30 dBA, which is quiet enough to rest and sleep. In a quiet living room, relaxing, the sound pressure level might be 40 dBA. A normal conversation at 1 metre would typically be 60 dBA. A tractor would be 78 to 95 dBA. An amplified rock music, which is getting very loud and could damage your ears, would be around 110 dBA. And a jet taking off at 60 metres could be 120 dBA. Now you might have noticed I've added an A onto the decibel here. Basically, there are different weighting curves for decibels, and the A weighting is to simulate how our ears hear sounds. Basically meaning that our ears are less sensitive to the lower frequencies than the higher frequencies, so we put an A weighting on it. So we're simulating what the ears actually perceive. So let's look at these weighting curves for sound pressure levels. As I mentioned, the A weighting curve simulates how our ears perceive sound. Our ears are less sensitive at the lower frequencies. So there is a weighting, or a negative weighting, to the sound pressure level at these frequencies. So if you look at 1 kilohertz and below, there's actually a negative correction in the different third octave bands for how our ears hear that sound. So at 63 hertz, we basically have about a negative 27 correction to the sound pressure level that we're hearing to account for how less sensitive our ears are to those frequencies of sound. Conversely, at 1 kilohertz and above, our ears are much more sensitive to these higher frequency sounds. So we're much more distracted or irritated by squeals and whines of sound, and these are the higher frequencies of sound. So you can see there's actually slight positive correction at the higher frequencies to account for this increased sensitivity to these sounds. There's another curve plotted on this graph here called the C weighting curve, the green line here. The C weighting curve is often used when you are trying to account for the subjective loudness of low frequency sounds. As you can see, there's very little correction or no correction at the low frequencies for sound pressure levels. This unit of measure is used to measure music noise. So if you're trying to measure music disturbance at a nearby residence, the C weighting curve is used to account for the low frequency content or the bass content of sound that is common in amplified music. So just be aware for sound pressure levels, if you see an A or a C on the end of the decibel, that they have been weighted according to the type of sound source or the receiver that is being taken into account. The A weighting simulates how our ears perceive sound, and the C weighting accounts for subjective annoyance or irritation from low frequency sound.